Section 2.8, Solving Linear Inequalities. Here at the beginning of the section, we have a brown box that defines linear inequalities for us. And if we look, it says a linear inequality in one variable, here in x, can be written in the form ax plus b is less than c, or less than or equal to, or greater than or equal to. So these are going to look like linear equations, but instead of having an equal sign, they will have some inequality symbol. Linear still means that our variable, x in this case, is raised only to the first power, and that x is the only variable in the problem. Everything else will be numbers. Now, before we jump on solving these inequalities, let's talk a little bit about notation. If I write x is less than 3, I can graph this on a number line. X is less than 3. I want to graph all of the numbers. I want to put a dot on every number that is less than 3. Well, 2 is less than 3. So is 2.5. So is 1.5. So is 1. So is 0. So is -1. So is 2.99. But not 3 itself. And nothing to the right of 3 on the number line is less than 3. To indicate this, we will shade in. We will color in all of the numbers below 3 or to the left of 3 on the number line. We will also shade in the arrow to indicate that this goes on and on forever in that direction. Now, it's hard to tell if we're actually including the 3 or not in this graph. And so what we agree to do is, if the 3 is not included, we'll put a parenthesis on the graph, opening in the direction of shading. If I wanted to include the 3, x is less than or equal to 3, well, again, I would shade everything smaller than 3 to the left of 3 on the number line, shade in that arrow as well, but this time indicate that the 3 is part of that set by using a square bracket. So if I see this equal bar, I should see a square bracket in my graph. Another way to write these sets of numbers are as intervals. An interval, let's just put a graph up here. Let's talk about all the numbers between 4 and 5. All the numbers between 4 and 5. Well, we'll shade in everything between. And I said all the numbers between 4 and 5. So we're not including the 4. We're not including the 5. So they get parentheses. Interval notation, we simply list the small endpoint, comma, the big endpoint. If the 4 is not included, I put a parenthesis on it. If it were included, I'd use a square bracket. My 5 is not included, so I'll use a parenthesis there. How would we write x is less than 3 then in interval notation? What is the leftmost endpoint? What is the boundary on the far left? Well, this heads all the way down to negative infinity. And now I know how to draw an infinity, and that one's not very good. After I do this several times in one lecture, they get sloppier and sloppier. So I've adopted this method from my high school geometry teacher. I just make 2 circles side by side. That's my handwritten infinity sign. Negative infinity all the way up to the 3. not including the 3, and you never include an infinity. Infinity, you can't get there, so you can't include it in this interval. My interval for x is less than or equal to 3. I'm talking about all the numbers between what? Negative infinity and positive 3, never including the infinity, but this time including that boundary point, the 3. Once I have a graph, it's usually very easy to come up with this interval notation. Let's look at a couple more. Let's talk about x is greater than or equal to 6. Why don't you pause right here, draw the graph, and give the interval notation. The graph, we want to shade in everything that is 6 or bigger, greater than or equal to 6. So, everything above or to the right of 6 on my number line, shade in that arrow as well. That indicates that the graph keeps going. If you don't shade in the arrow, strictly speaking, that would not be right. And then because the 6 is included, it says x can be equal to 6. I'll use a square bracket. There's my graph. My interval, I'm talking about all of the numbers between 6 and what? On this side, positive infinity. I don't need a plus sign, just an infinity. Include the 6. Never include an infinity. We can even do this for all real numbers. My graph for all real numbers, shade them all in. Real numbers are the numbers that are on the number line. So shade in the entire number line. And my interval notation, I'm talking about all the numbers between negative infinity and positive infinity. Infinities always get parentheses in interval notation. So notice on page 175 in your reading here at the bottom, you have a blue box you need to look over, and you have a table at the bottom that talks about methods of expressing solution sets. And they even talk about the set builder notation, which, just for a quick example, the set of all x such that x is greater than or equal to 6. There's the set builder notation that we've talked about before. The set of all x such that, and then we state a condition. But in this section, we're going to primarily focus on the interval notation. Now, before we solve these inequalities, I just want to think about a problem. Let's say that x plus 2 is greater than or equal to 5. And let's do this the first grade way. Let's just think about it for a minute. What would x have to be for this statement to be true? A solution is a value I can plug back in that makes the original statement true. What could I plug in for x that would make this true? Would 3 work? 3 plus 2 is 5, and that is equal to 5, so yes, 3 works. What if I plug in 4? 6 is greater than 5, so that works. Plug in 5 or 6 or 7. Plug in something bigger than 3, add 2 to it, and you've got something bigger than 5. What if I plug in 2? 2 plus 2 is 4. That's not greater than or equal to 5. And so what we figured out is that anything 3 or bigger will make the original statement true. Take something 3 or bigger, add 2 to it, you will get something that is 5 or bigger. We're talking about all the numbers that are greater than or equal to 3. My interval notation, I'm talking about all the numbers between 3 and positive infinity, including the 3. Now, doesn't it look like we could solve this like we solve an equation? That is, let's subtract 2 from both sides. Subtract 2 from both sides, and that will give us x is greater than or equal to 3, which is what we ended up with, just thinking about it. So I've got to wonder, is that going to work every time? Let's consider a few inequalities and see if we can manipulate them and determine if that will work. Let's take the inequality 2 is less than 3. And I'm going to want to do this several times because I want to check several different things. If I add the same amount to both sides, the result, 7 is less than 8, that's a true statement. If I subtract the same amount from both sides, let's subtract 6 from both sides. That gives me -4 is less than -3. That's a true statement. If I multiply both sides, let's say I triple both sides, multiply both sides here by 3. Multiply both sides by 3, and that'll give me 6 is less than 9. That's true. Let's multiply both sides by a negative number. Let's multiply both sides by, say, -4. Multiply both sides by -4. That gives me a -8 on the left, a -12 on the right. -12 is the smaller of these two numbers. -12 is the smaller. And so, for this to be true, I would have to have a greater than sign there. It turns out that solving inequalities is exactly like solving equations, with one exception, and that is right here. If you multiply or divide both sides by a negative number, you must switch the sense of that inequality sign. You'll have to turn him around. If he had an equal bar to start with, he would keep his equal bar. You just turn him around. You can add, subtract, multiply, divide both sides of an inequality just like an equation, except if you multiply or divide both sides by a negative, you must switch the sense of your inequality so that your next step is still true. Let's look in the book. Here on page 176, the addition property of inequality. And this looks essentially like our addition property of equality back in section 2.1. If A, B, and C represent real numbers, then the inequalities A is less than B and A plus C is less than B plus C are equivalent. That is, they have the same solution set. Notice our little star, our little asterisk here says this works for less than or equal to, it works for greater than, it works for greater than or equal to. It's simply given here in terms of less than. And what this allows me to do is add or subtract the same number on both sides of an inequality without changing the solution set. Now, our brown box for the multiplication property of inequality. It's got a little more going on here. Multiplication property of inequality. It says, let A, B, and C be real numbers where C is not 0. Now, if C is positive, A is less than B and AC less than BC are equivalent. What does that allow me to do? It allows me to multiply both sides of the inequality by the same positive number. All right. Part 2 says, but if C is negative, then these two inequalities are equivalent. A is less than B is equivalent to AC is what? Greater than BC. So if you multiply both sides by a negative, what? You must switch the sense of your inequality. Since it works for multiplication, it will also work for division, as we discovered back in section 2.2. So solving inequalities is essentially the same as solving equations with one exception, and that is, if you multiply or divide both sides of an inequality by a negative number, you must switch the sense of your inequality. Let's try some homework problems. In your reading, be sure and look over that blue box that we have on page 179. In the homework, let's grab number 20. The instructions say solve, but it goes on to say to write the solution set in interval notation and graph it. Now, frankly, I would do the graphing before the interval notation, because once you have a graph, that interval notation, that's easy to come up with. Solving an inequality is just like solving an equation, with one exception. If you multiply or divide both sides by a negative number, you must switch the sense of your inequality. So our goal here is to get p by itself on one side. We'll do that by adding 3 to both sides, just like we would an equation. On the left-hand side, the 3's subtract out to leave simply p. On the right-hand side, negative 11 plus 3 is negative 8. And we did not multiply or divide by a negative, and so we leave our inequality alone. We've got p by itself on one side. This is solved. If all I said was solve, you could put a box around that and be done. That is solve for p. But she said to write the interval notation and to give a graph. I like doing the graph first. Mark my point of interest. We're talking about all values of p that are what? Greater than or equal to negative 8. Greater than is above or to the right. We'll shade that in. Equal to, we show with a square bracket on our graph. So, our interval notation, we're talking about all the numbers between negative 8 and positive infinity, this time including the negative 8 and never including an infinity. She wanted both the graph and the interval. Now, quite frankly, on a quiz or a test, I most often just ask for the interval. I typically will only ask for the interval, so that's all you would box in. But she asked for both, so we'll put a box around both. Let's talk a little bit about terminology. If I have an interval that has parentheses on both ends, that is, includes neither endpoint, I call this an open interval. If I have an interval notation that includes one endpoint but not the other, I call this half open. These are not terms that you're responsible for, but you will hear me use them in lecture. If I have an interval that includes both endpoints, I will call this a closed interval. So, when I write this final answer here, my interval notation, you might hear me say, so our solution set is the half-open interval on negative 8 to positive infinity. The half-open interval on negative 8 to positive infinity. And in this case, I don't have to tell you it's being half open. I don't have to tell you which side the square brackets go on, because infinity is never included. Infinity always gets a parenthesis. The other thing you should make note of, in interval notation, the smaller number is always on the left. The larger number is always on the right. If you turn that around, it makes no logical sense to interpret that as an interval, and it will be counted wrong. Small number always on the left, big number always on the right. Let's try number 24. Again, we're asked to solve, giving both the interval notation and the graph. And even if all I ask for on a quiz or a test is the interval notation, I still recommend that you draw a graph just because it makes the interval notation so easy to come up with. We want to solve this for x. Just like we would an equation. We'd say simplify both sides. Both sides are already simplified. Get x on one side. Get x on one side. Subtract 4x from both sides. We subtracted. We're not multiplying or dividing by a negative, we're just subtracting, and so we leave our inequality symbol alone. And then get x by itself, add 2 to both sides. And we find that x is less than negative 3. There's our solution, but she wants the graph in the interval. So we'll graph this. Our point of interest, our boundary point is the negative 3. We're talking about all x's less than negative 3, smaller than, or to the left of negative 3 on the number line. We'll shade those in, including the arrow. This time, the boundary point is not included. It's not or equal to. It's just less than. And so we'll use a parenthesis on our graph. Our interval notation, this is the open interval on negative infinity to negative 3. She wanted both the graph and the interval. If all I ask for is the interval, please just box the interval. Even if you draw a graph to help you get that interval, just box what I ask for. Number 42. We want to solve this inequality for x. Again, she wants the graph and the interval as part of our final answer. Both sides are already simplified. X is already on one side. Let's get x by itself. Add 4 to both sides. Add 4 to both sides. That gives me negative 5x is less than 10. And now to get x by itself, divide both sides by negative 5. Divide both sides by negative 5. And so we're seeing it now. We've divided both sides by a negative. That requires that we switch the sense or the direction of our inequality. Our less than becomes a greater than. And our solution, this will give me x is now greater than negative 2. X is greater than negative 2. My graph, everything above or to the right of negative 2 on my number line. There's no equal bars, so I use a parenthesis on my graph. And my interval, we're talking about the open interval on negative 2 to positive infinity. Next semester or in future classes, instead of seeing parentheses and brackets, what you might see is an open circle where we would use a parenthesis that says it comes right up to it and stops but does not include it. And then if I had x is greater than or equal to 4, instead of a square bracket on the graph, what you may see, depending on the textbook and the instructor, you may see a solid dot to indicate that. We'll stick with parentheses and brackets for now, but just be aware, this is some notation you might see later down the road. Let's crank it up just a little bit and try number 48. Under the same instructions, so we're solving, giving that graph, and giving the solution set in interval notation. Simplify both sides. That's already done. Get x on one side. I want to work this problem two different ways for you. I want to first bring my x's to the left and see what I get, and then start over, and next time take my x's to the right. Let's work this one taking my x's to the left. Add 4x to both sides. Get x by itself. Subtract 1 from both sides. We're not multiplying or dividing. That's just a subtraction. And so we leave our inequality symbol alone. It remains less than. And divide both sides by -4. Now we're dividing by a negative. That means I've got to turn my inequality symbol around. On the left-hand side, the -4's cancel to leave just x. On the right, positive divided by a negative is negative. 10 divided by 4, best I can do is reduce. -5/2. Okay, so let's remember this. Let's pop this over here. So that's what we got, taking our x's to the left. What happens if I work this same problem, but this time I take my x's to the right? Add 8x to both sides. We now have x on one side. Let's get x by itself. Subtract 11 from both sides. -10 is less than 4x. And divide both sides by +4. Now dividing by a positive leaves our inequality symbol alone. So we will have x is greater than. Okay, now did you see what I did? I'm reading from right to left. I'm reading from the x side. X is greater than whatever this guy is, right? I mean, if 2 is less than 3, isn't that the same as saying 3 is greater than 2? This is going to give me x is, well, here on the left, a -5/2 again. -5/2 is less than x. That's the same as x is greater than -5/2, which is what we got before. So if you solve an inequality, it is considered generally best practice to end up with your variable on the left-hand side. And that simply means if you get to the bottom and you've collected your variable on the right, turn the whole inequality around. If this is less than that, then that must be greater than this, right? Just like my 2 and my 3. That makes it much less likely that you're going to make a silly mistake graphing. We're talking about all the numbers right here. I don't want to look at this less than sign because I'm liable to shade the wrong direction. I want to see it when x is on the left of my inequality. X is what? Greater than this boundary point. Those are all the numbers that are bigger or to the right. There's no equal bar, so we're not including that endpoint. And our interval is the open interval on -5/2 to positive infinity. And it didn't matter which way we worked it. It turned out the same either way, no matter what side I took the variable to. Let's have a look at number 62. Number 62. Solving equations is just like solving inequalities. Solving inequalities is just like solving equations, with one exception. When you're solving an inequality, if you multiply or divide both sides by a negative number, you must switch the sense of your inequality. We know that we can clear fractions from equations. Can we clear fractions from inequalities? Sure, it's got two sides. So we can multiply both sides by the same thing, still have an equivalent inequality. Let's multiply both sides by the least common denominator. That would be 6 this time. On the left-hand side, how many terms were there before I put the pink parentheses in place? How many terms are on the original left-hand side? That is, how many rainbows am I going to have to draw to distribute? There are 2 terms separated right here. So I will distribute this 6 to the first and to the second term. On the right, we're just multiplying. In fact, let's go ahead and knock that out. Half of 6 is 3. Here on the left, 6 times 1/6 is 1 times x is just x. Plus 6 times 1/3, or 1/3 of 6, or 6 divided by 3, right? 6 divided by 3 is 2, times 1 is 2, and times the rest of it. That pink 6 never makes it in the little black parentheses. It is completely absorbed by that 1/3. Very careful. We've cleared the fractions. Let's get both sides simplified. The right-hand side is ready to go. The left-hand side needs some work. Let's distribute this 2. Combine like terms. We have both sides now simplified. And so we want to get x by itself. We will add 2 to both sides. And divide both sides by 3. We're dividing by a positive number, so we don't have to switch the sense of our inequality. And of course, 5 divided by 3 is what? 5/3. There's the solution, but she wants the graph and the interval. So my graph, everything above or to the right of 5/3 on my number line. There's no equal bar, so we are not including this boundary point. We'll use a parenthesis. And my interval is going to be, well, what have I shaded between? Everything from 5/3 up to infinity. We're not including the endpoint, and we never include infinity. So we have an open interval there. They work just like equations, with that one exception. If you multiply or divide by a negative, you switch the sense of your inequality. Now I want to look at some of what are called triple inequalities. Think about this. I'm thinking of a number between 1 and 10. What does that mean? I'm thinking of some number x between 1 and 10. Well, that means it's got to be bigger than 1. And if it's between 1 and 10, it's got to be less than 10. Remember, between does not include the endpoints. Between does not include the endpoints. What number could I be thinking of? Maybe 5. Maybe pi. Maybe square root of 11. We have infinitely many numbers between 1 and 10. And how would I show this on my number line? On my number line, I would show my boundary points, the 1 and the 10. We're talking about all the numbers that are bigger than 1 and at the same time smaller than 10. Where do those overlap? Well, again, between 1 and 10. We're not including the 1. We're not including the 10. We're talking about the open interval on 1 to 10. Another way to write this compound inequality is to write that I'm thinking about x's that are less than 10, and at the same time, watch this, and at the same time x is greater than, because I'm reading right to left, x is greater than 1. So here's a triple inequality. It says two things at the same time. It says x is what? Greater than 1, and at the same time x is less than 10. We read this saying x is between 1 and 10. If we had included one of the endpoints, we would have used a bracket here, and I would have a half open interval. I would say I'm talking about all the numbers x between 1 and 10, including the 1. And when I talked about my interval, I would say I'm talking about the half open interval on 1 to 10, including the 1. Because if I don't tell you which side the bracket goes on this time, you won't know. If I had included them both, brackets everywhere, we're talking about all the numbers between 1 and 10 inclusive. Inclusive tells me I'm including both endpoints. I'm talking about the closed interval on 1 to 10. Saying that it's closed, seeing these brackets, tells you I am including those endpoints. Well, guess what? We can solve critters that look like this. Because think about it, it's just two inequalities that have been squashed together. Look at problem number 102 in the homework. We have a triple inequality. We have a triple inequality or a compound inequality. Our goal is to get x by itself in the middle, so we can say x is between this and that. This is just two inequalities shoved together. So I can still use the addition and multiplication properties of inequalities. It's just now, instead of saying what I do to one side, I also do to the other, I say what I do to one part, I must do to all three parts. You see, because I'm working two different inequalities at the same time. What I do to one part, I must do to all three parts. Our goal is to get x by itself in the middle. Let's add 4 to that middle. What I do to one part, I must now do to all three parts. This gives me a negative 3 is less than or equal to, just 3x now in the middle, is less than or equal to 12. And divide by 3 to get x by itself. What I do to the middle, I've got to do to all three parts. We're dividing by a positive, so our inequality symbols are unaffected. This gives me negative 1 is less than or equal to x is less than or equal to 4. And we would read this by saying x is between negative 1 and 4 inclusive. Our graph, we'll shade in everything between negative 1 and positive 4. We are including both endpoints with those equal bars, so they both get square brackets. My interval is the closed interval on negative 1 to positive 4. She had asked for the graph and the interval notation. Let's look at number 106. A triple inequality. Our goal is to get the x by itself in the middle. To do that, I need to divide by negative 3. What I do to one part, I must now do to all three parts. And on top of that, I'm dividing by a negative. That means I must switch the sense of my inequality signs. This will give me a negative 3 is greater than x is greater than negative 5. Now, what did we say about intervals? How do we always write intervals? With the smaller number on the left. Triple inequalities it is considered best practice to always write triple inequalities using less than symbols, or less than or equal to, like the previous problem. Turn the whole thing around. I want my smaller number on the left. That's going to keep me out of trouble. We've got -5, reading this backwards, is what? Is less than x is less than -3. Because, see, on a quiz or a test, somebody is going to look at that, and I don't always ask for the graph. They're going to say, oh, no equal bars, it's going to be parentheses, and it's between -3 and -5. And I'm going to count it wrong, because that's not what that says. Unless the smaller number is on the left, it doesn't say what you think it says. The smaller number must be on the left. So we might as well turn our triple inequalities around so that the small number is on the left. Let's finish this off with a graph. -5 to -3. Everything between, no equal bars, so we use parentheses. This is the open interval on -5 to -3. All right. Let's have a look at number 110. Number 110. Solving inequalities is just like solving equations, with one exception. If I multiply or divide by a negative number, I must switch the sense of my inequalities. Just like with an equation, we want both sides simplified. Well, in a triple inequality, we want all parts, all three parts simplified. Let's work on this middle part first. Let's distribute that 2. Although in a minute, let me come back and talk about another approach I could have used. Distribute the 2. Simplify all three parts. All right? Now get x by itself in the middle. Subtract 2. What I do to one part, I must do to all three parts. We're subtracting. We're not multiplying or dividing by a negative, so the sense of our inequalities will remain the same. And divide both sides by 2. I said both sides just because that's a habit, right? Divide all three parts. Divide all three parts by 2. In the middle, we've got x by itself, which is our goal. X is now going to be between, here on the left, I get a -3. On the right, I get a +2. And what? Including the 2. X is between -3 and 2, including the 2, because we've got an equal bar there. My graph, we're talking about everything between -3 and +2, not including the -3, so he gets a parenthesis, but including our boundary here at +2. So there's my graph. My interval, the half open interval on -3 to 2, including the 2. She wanted both the graph and the interval. Like I said, let me come back and talk about this again. We have standard approaches. We have blue boxes that give us a rough guide on how to approach these problems. But as long as we don't break the rules of algebra, we should get the same answer anyway. Here I started by distributing the 2. Then I subtracted 2 from both sides and divided both sides. I'm still saying both sides. I subtracted 2 from all three parts, divided all three parts by 2. But there's nothing wrong with this. Divide all three parts by 2. What happens? These 2's cross cancel. That's going to leave me negative 2 is less than x plus 1 is less than or equal to 3. And then to get x by itself, subtract 1 from all three parts. What's that give me? Same thing I got before, because I never broke the rules of algebra. So long as I don't break the rules, I should get the same answer. So that's just another approach that you can use on that particular problem. Let's finish up today with number 114. In number 114, we have a fraction. I think I'd like to clear that fraction. Although it's not the only way to do the problem. You could work it with the fraction in place, but I want to practice clearing fractions. You clear fractions from a triple inequality just like you do an inequality or an equation. Except now, instead of multiply both sides, it's what? Multiply all three parts by, and in this case, multiply all three parts by 4. In the middle, I'll have to distribute. So that's going to give me 8 is less than, distributing this 4, 24 plus, those 4's cancel, 3x, and is less than, that's going to give me 48. Let's get x by itself. Subtract 24. All three parts. That'll leave me a negative 16 is less than, in the middle, just 3x now, and is less than 24. And to get x by itself, divide all three parts by 3. We're dividing by a positive, so our inequality symbols will be left alone. Negative 16 thirds, less than x, less than 8. There's our solution, our graph. And with the graph as well, smaller number on the left. Smaller number on the left. Shade everything between. We're not including either endpoint. We're talking about the open interval on negative 16 thirds to positive 8. Now, truth be told, this problem would not be too tough to work with the fractions in place. Let me just show you very quickly. Remember what we got right here. Okay? X is between negative 16 thirds and positive 8. If I choose to leave that fraction in place, it's really not that tough to work with this time. Since there's only one fraction running around, there's not a whole lot to worry about. Try to get x by itself. Subtract 6 from all three parts. That gives me negative 4 is less than 3/4 x is less than 6. And now to get x by itself, what? Multiply all three parts by the reciprocal of that coefficient. Multiply all three parts by 4/3. So in the middle, the 4's cancel, the 3's cancel to leave x. X is between. Here on the far right-hand side, do you want to see that 6 over 1? 3 goes into 6 twice. 2 times 4 is 8. Over 1, we don't write the over 1. And over here, what do we have? You want to see that negative 4 over 1? Nothing will cross cancel. 4 times negative 4 is negative 16 over 3 times 1 is 3. Same thing that we got before. So with this problem, I really want you practicing clearing fractions because of how important that is to us later down the road. But for this particular problem on a test or a quiz, if you think it easier to leave the fraction in place, do it. Just remember, in Chapter 6, we will no longer have the option. We will have no alternative but to clear fractions from equations. That's our look at 2.8. Get started on that homework.